Here's an example of solving an equation using the sum and difference formulas. Solve sine of x cosine of 2x minus cosine x sine of 2x equals negative root 3 over 2. Now once again, this is part of pattern recognition. When you see this combination, something should be going off in your head that this pattern looks familiar. Sine cosine minus cosine sine. And so you have to either remember the formulas, or I've got them written down here, which formulas, or which formula does it match with, and then what are the values of alpha and beta. So I'm going to write underneath it, we have a combination of sines and cosines, so we'll do sine alpha cosine beta. Now you'll notice that here we have a minus sign up here and plus sign down here, so we know we're going to have to flip the sign when we actually make the substitution. Cosine alpha sine of beta. Right, so we can see that alpha is x and beta is 2x. And that this whole thing is actually going to be equal to sine of alpha minus beta, right? Again, minus sign here because the sign's flipped relative to that formula. Okay, so we now know what this is, and we know that alpha is x and beta is 2x. So this whole thing becomes sine of x minus 2x is equal to negative square root of 3 over 2. Well, x minus 2x, that's sine of negative x. And now here we have to think some more. Sine of negative x, the negative angle identity. What does that tell us about this expression? Well, sine is an odd function, so the negative sign factors out. Negative sine of x equals negative root 3 over 2. So sine of x is square root of 3 over 2. And now we're getting somewhere. Now we've got this down to a very simple trigonometric equation. We know how to solve this. Let's take a look at our unit circle picture, right? So sine is the y-coordinate, and we want the y-coordinate to be positive. That's going to give us solutions in quadrants 1 and quadrants 2. The reference angle, sine of what is equal to root 3 over 2? You'll remember that's going to be pi over 3, as that tells us the other angle is pi over 3, or the other reference angle is pi over 3. So x is equal to, we've got pi over 3. The other angle, we have to go full pi to get to here, and then pull back by pi over 3. That's going to be 2 pi over 3. And in this case, you see that there's no restriction on the solutions, and so we have to remember the plus 2 pi k. And that gives us the solutions to this equation. Right? So again, the starting point was just recognizing this form, recognizing this pattern. And with more practice and more experience, it'll become easier and easier to recognize these things. Here's an example of proving an identity using the sum and difference formulas. Now here is identity, and you might recall that when we prove identities, you start from one side and you work your way to the other. Now whether you work left to right or right to left will depend on the problem. And typically we try to look for the side that is more complicated and move towards simpler. In this case, they're roughly equally complicated. This is a mixture of tangents being added and subtracted. Here you have these new formulas to work with. So it doesn't really matter sometimes if you're in this case, and you just try one and get started. I will say that if you start from this side, you can start by substituting in the formulas, and it's going to be more sort of thinking about the algebra. If you start from this side, you're going to do some algebra first, and then you're going to have to rely on pattern recognition to see that you've actually got these formulas in play. And so, again, it's up to you. I'm going to start from the left and work my way to the right. So, sine of a plus b over sine of a minus b. Okay, well, let's make our substitution. Sine of a plus b is going to be sine of a cosine of b plus cosine of a sine of b. And in the denominator, it'll be the same thing, except for we'll have the sign flipped. And so we'll have sine of a cosine of b minus cosine a sine b. Now remember that when you're working with fractions, you cannot break this up into a bunch of different parts. So some students will start canceling things out here and it just becomes a mess. Remember that you can't cancel out unless you have a product of terms on the top and on the bottom, and those terms that you're canceling out are identical. Okay, so what's going to happen here? Well, in this case, we have to take a look at where our goal is. Our goal is to get tangents over here. And if you take a look at what we've got, we don't have anything that looks like tangents. In order for us to have tangents, we need cosines in the denominator. So one way we can handle that is that we can multiply top and bottom of the fraction by the same thing to create those fractions. So sine A cosine B minus, plus cosine A sine B. And then on the bottom, sine A cosine B minus cosine A sine B. And we're going to multiply top and bottom by something, some sort of fraction. And since we want tangent A and tangent B, and that has a cosine A and cosine B in the denominator, right, sine over cosine, we're going to just try that and see what happens. So cosine A cosine B gets really squished over here on the side. That happens sometimes. So we multiplied the top and the bottom by 1 over cosine A cosine B. Now, really important here, we're going to have to use the distributive property, multiplying this by the entire numerator here. So what do we get? Well, if we look at this first term, well, actually, I'm just going to write it out. Sine A cos B over cos A cos B, and similarly for the rest. Cos A sine B over cos A cos B, in the denominator, sine of A cosine of B over cosine A cosine B minus cosine A sine B over cosine A cosine B. Having written this all out, we now just look for cancellation. Here we have a cosine B canceling out. Here we have a cosine A canceling out. And then same thing here. Cosine B's cancel out, cosine A's cancel out. And what are we left with? Well, here we have sine over cosine, sine of A over cosine of A, which is tangent A, plus sine B over cosine B, tangent B, all divided by sine A over cosine A is going to be tangent A. Denominator has a minus sign, tangent B, and that's exactly what we were going for. So this is a trick for these types of proofs. In this case, remember, we had to think about where we are going to. We wanted to get tangent terms, and so we needed to get cosines to appear in the denominator somehow without changing the value of the expression. And so that's what this step right here, multiplying by something over itself.